started. Okay, so polynomial and rational inequalities is the title. Polynomial and rational. So remember, polynomial is just a function, you know, like x plus 2 or 3x squared minus 5x plus 6. Inequality would mean that it's greater than 0 or less than or equal to 0, like that sort of thing. That's a polynomial inequality. That second one looks really easy to solve. Okay? Rational inequality would be more like this. 3x plus 5 over x minus 2 is less than 0. Solve for x. Or 3x plus 5 over x minus 2 is less than 5. Solve for x. The second one is quite a bit harder than the first one, even though they look about the same difficulty. But the first two black ones there, those are polynomials, and they're inequalities. And the two purple ones there are rational functions, and they're inequalities. See? Okay, so that's kind of what the questions look like. You will see either problems like x squared minus 3x is greater than 12, something like that. Actually, probably not a 3x here, probably just an x. Okay, something like that. Or you'll see something like this. X plus 5 over x minus 3 is greater than 0. Or x plus 5 over x minus 3 is greater than 5. See? Okay, so that's what they look like. Now, what I want to show you is that all of these can be written in the same form before starting. So, like this one, you could write it as x squared minus x minus 12 is greater than or equal to 0. And this one can be written as, well, it's already greater than 0. See? And this one could be written as x plus 5 over x minus 3 minus 5 is greater than 0. So the goal on this, actually the first goal on every problem is to get a big fat goose egg on the right. That's a really important step. Okay, it's a really, really important step. And so the first thing we always do is subtract all the junk to the left side. Okay? All right. What do the problems mean? Okay? So if you are given something like this, x squared minus x is greater than or equal to 12, bless you. We know it can be written like this, x squared minus x minus 12 is greater than 0. Bless you again. You see, it can be written this way, and this has a very particular meaning. Bless you. This is like an f of x is greater than or equal to 0, see? What's another way to think of f of x? Y. Yes. So this means the function's greater than 0, which in turn means y is greater than or equal to 0, which means there is this graph, okay, of f, and we're looking for the parts that are above the x-axis. It means above x-axis. For example, in this problem, the easiest way to solve this problem, I think, is just to factor it. X minus 4, x plus 3, see? You now know where the x-intercepts are. They are at 4 and negative 3. So you can just go 1, 2, 3, 4, left, 2, 3. You can put them on here. It's a happy parabola. See? And what we are trying to find, because it said greater than 0, is f of x greater than 0, which means y is greater than 0, which means above the x-axis, which means my answer is actually just this green part here. And the way I write my answer is to give the x's that make this true. So the x's that are greater than or equal to 4, I mean. The x's that are greater than or equal to 4 show this quality, where y is greater than or equal to 0. And over here, the y's that are, the x's that are less than or equal to negative 3 show this quality, where y is greater than or equal to 0. So my final answer is an x answer, but it's a description of y, you see. I'll run through that again. This problem can be written like this, which means f is bigger than 0. F is bigger than 0 means y is bigger than 0. Y is bigger than 0 means above the x-axis. On a plot like this, that would be these two slices. And this is how you describe it, giving me x's only. Okay? So that's what the problems all mean. Now, how would it change if this was a less than or equal to? How would that change our meaning? First of all, this would be a less than or equal to. Oh, I can't draw that backwards very well. But this would be a less than or equal to, right? This would be f of x is less than 0, which means y is less than 0, which means what? Below the axis. See? And then your answer would be what? This piece, you see. And you would give me a different answer. You would say, Mr. Shore, the answer is between -3 and 4. So this will become more clear as I do examples, but every problem can be converted into a y is greater than 0 or a y is less than 0 problem. And then interpreted as either an above or a below type problem. And then answered using a domain. Okay. All right, some examples would be like the one we just did, of course. Or what about this one? X cubed minus 2x is less than, 2x squared is less than 8x. Okay, so what it really means is quite complicated. If you just look at this, it's like you've got this weird cubic curve, and then you've got this line called 8x, and they look like that together, and you're trying to find where this graph is below that graph. Forget that. Bring everything to one side, okay? So that it looks like a y is less than 0 problem. Factor it if you can. This one factors nicely. And then there are kind of two philosophies for finishing this, okay? One philosophy is to use kind of the number line thing I just showed you. Only this time there are 3 interesting numbers here. What are they? 0, 4, and -2. So you can take this purple solution, okay? Or I'll show you a different way to look at it in a second. So you just plot these on here, and don't get carried away. Okay, some people get really carried away with the number lines. Just draw the numbers on a number line. I don't even care if they're spaced properly. And now everything is multiplicity 1, right? The x minus 4, the x plus 2, they're all odd in multiplicity. So just test any one region you want. So why don't we test 10? X equals 10. Test x equals 10. 1,000 minus 200 is less than 80. Is that true? Last period, someone said it was true. Someone was like, true. Are you sure? 800 is less than 80? Okay, that's false. So evidently 10, which is out here, is not going to get shaded. Okay, so since it's odd multiplicity, then that means the next region over will be shaded. And then the next region will not be shaded. And then the region after that will be shaded. And we've got the answer to the problem. This is the full solution to the problem. It's just in graphical form. So now what we're going to do is just write it down. We got x is less than -2. 0 is less than x is less than 4. Or you can use the cool interval notation. -infinity, -2. 0, 4. Doesn't matter to me. Okay, there's a totally different way of looking at this. And it would be really good to see both ways together. So here's a totally different approach. You look at this and you say, this is like an f of x is less than 0 problem. Right? the function is clearly x times x minus 4 times x plus 2, which is obviously a cubic. And you can actually sketch the full polynomial. What does this cubic look like? Well, it has one x-intercept here at negative 2, there's one at 0, and there's one at 4. Oh, thank you. I need to move my projector a little bit. Cubics have the end behavior like this. Remember with your arms? So you have one arm down, one arm up, and the leading term is a positive x cubed. So left arm down, right arm up. So you already know that the general shape is like this. And these are all multiplicity 1, which makes them all crossing points. So we're bringing in our background knowledge. And this means y is less than 0, right? What does y is less than 0 mean? Above or below the x-axis? Below the x-axis. So you would automatically then be interested in this region here and this region here, see? And you would conclude the same exact thing as before. X is less than negative 2, x is between 0 and 4. Same conclusion, slightly different visual, but they really both mean the same thing. This is sort of a one-dimensional representation of the facts. This is a 2D version. I think you need to see both and mean the exact same thing. What I shaded in green here is the exact same intervals I shaded here in green. So whenever possible, do both on the test, on the homework. That way you're always reinforcing what everything means. Okay? You don't want to just do number lines 15 times and think you get it. You want to see what the sketch looks like. All right, let's try an example of a rational one. That's where it looks like a fraction. Okay? So you really can just make these up. So I'm just going to make one up. My second example is x minus 1 over x plus 2 is greater than 0. Okay? Now, if you really want to, you could carefully and meticulously plot this thing and see what it looks like. You are looking for values of x that make f of x greater than 0. In other words, y is greater than 0 or above the x-axis. So if you know what this means, then you know what you're looking for. And your sketch will lead you right to the answer. By the way, if you are a fan of sketching, I suggest long division first, and you'll see the transformations needed to move 1 over x into its right location. But I wasn't planning on using transformations to graph this. I was actually planning on just analyzing the function. So first thing I notice about this problem is the number x equals 1 is a root of this rational function. That means if I just graphed this f of x equals x minus 1 over x plus 2, that thing is an x-intercept. Which is an important point, because at an x-intercept, it's very likely the graph will cross through the x-axis, one side negative, one side positive, see? So that's a critically important value. I won't say a critical point. But it's very important, and I need it. And it's going on my number line. There's another number that I think is very, very important. Negative 2. Negative 2 is called a pole. It's called a pole of the rational function. It's really just, all it really means is the root of the denominator. But it has a name of its own. And basically, that's an important number because on the different sides of the pole, I'm going to have different behavior. Watch. Let's say you go up here to x equals 1, right? If you plug in 1.1, the top is positive and the bottom is positive. But if you plug in 0.9, the top is negative and the bottom is positive. That's different, right? But going down the bottom, if you plug in negative 2.1, the top and bottom are both negative. But if you plug in negative 1.9, which is just on the other side of negative 2, then the top is negative and the bottom is positive. See? So my function will behave differently on either side of these two numbers, you see. So how did I get them? Easy. I just looked at the roots of the top and the bottom and I wrote them down. But I believe they're important, and I'm going to put them on my number line. By the way, if you think a number is important and you put it on the number line and it turns out it's not important, no harm done. It doesn't hurt at all. As long as you're carefully testing everything, you'll still get the truth in the end. Okay, so here are my 2 points. Just put them on my number line. Now this is a strict inequality, so I'm going to make them open points. And I'm just going to test one value because I'm lazy, and multiplicities are all odd anyway. 0 it is. So if I plug in 0, I get 0 minus 1. 0 plus 2 is greater than 0. That is false. Negative 1/2 is not greater than 0. So I'm not going to shade the middle. I'll shade the other side of 1 and negative 2. Okay, now, it would be a good idea to at least visually understand, or like graphically understand what this means. Now, is this a y is less than 0 or a y is greater than 0 problem? This is a y is greater than 0 problem. Is it an above the x-axis or below the x-axis problem? Above. Okay, so what this means is the purple shading that I did represent regions of aboveness. See? So this is above, and this is below, and this is the above. And when I say below, above, I'm talking about the x-axis, of course. Okay? So somehow this graph must look something like, we don't have to get it perfect, but I believe with all my heart that this part of the graph is above the x-axis, this part is below the x-axis, this part is above the x-axis, see? That's what I believe. Now, is that the right shape? No, not at all. In fact, this is a vertical asymptote. Okay? And x equals 1 is actually an x-intercept. So my graph is horrible, but it still represents the truth that the regions that are above, and the regions that should be below are drawn below. I can actually tidy this up a bit by doing my rational function analysis from page 234, you know. And you would see that this actually has a horizontal asymptote up here at 1, okay? And it looks something like this. See? And the regions that are above the x-axis really are matching with my number line up above. Now, I don't need you to draw the actual graph like this. The number line is sufficient. I need you to understand. I need you to kind of understand what it means. Above and below is what it means. In this case, shaded meant above. Okay, what happens if instead of having a 0 on the right at the beginning of the problem, what if it was like a 5? That's the only thing left that I haven't explained. So this is the last example. Let's do the exact same problem, only this time it's x minus 1 over x plus 2, and it's going to be greater than 5. So is this harder? It is actually quite a bit harder. So the first thing is, the rules I'm showing you today only work when the right side is 0. Okay? So at first glance you might think, oh, I'm going to put 1 and negative 2 on a number line. Don't be too hasty on that. Let's put this in the right form. Move the 5 over so that it looks like that. Then collapse this into one fraction. Okay? Collapse it into one fraction. So you can just basically think of this as 5 over 1. Get that combined. So I'm going to multiply top and bottom of the second term by x plus 2. See? After it's collapsed, I'll be able to draw that number line. Okay, so it actually looks like my numerator is x minus 1 minus 5x minus 10 over x plus 2. My denominator is x plus 2. So it's actually negative 4x minus 11 over x plus 2 is greater than 0. Now I can clearly see what my critically important numbers are here. The root is negative 11/4. By the way, that's negative 2.75, if you're curious. And the other important number is my pole, and that's just, of course, negative 2. So getting everything equal to 0, you know, and then getting it all into one fraction helps you really understand what to do. All right, I'll draw my number line down here. See, it's getting kind of too hard to actually sketch the curve. I'm just going to cheat and use a number line. I've got negative 2.75 on here. I've got negative 2 on here. These are both open points. And we'll test maybe 0, because I like 0. Is 0 minus 1 over 0 plus 2 greater than 5? Because that's what the original problem said. X minus 1 over x plus 2 is greater than 5. This is false, isn't it? Okay, so I'm not going to shade 0. X equals 0 is over here. I'm not going to shade that region. I'm going to shade this one, though. And I can't shade the left side because everything's even odd multiplicity. So if this side of negative 2.5 is shaded, then this cannot be. See? And if this side of negative 2 is shaded, then that side cannot be. So we can now go ahead and verify it on the calculator. So I am willing to let you try it, graphing it. It's cool to see the final answer. So just turn it on. Type in your function. It was negative 4x minus 11 over x plus 2. Graph it. Now my answer for this problem was, remember, negative 2.75 is less than x is less than 2. So let's see if we can find that in this picture. I think I may have typed it wrong. This should be an 11. One of these days I'm going to learn to type, but I have to go back to school to learn it. So, okay, between negative 2.75 and negative 2. Still don't trust this thing. Okay, I trust it. So let me zoom in on the region. Let's do a window where x is just between negative 3 and maybe negative 1. Yes. Okay, so what I'm looking at here is this is x equals negative 2. This is actually our asymptote, see? And here is your root at negative 2.75. And the only part of the whole curve that is actually above the x-axis is this tiny little region. That's it, just that tiny little space. Everything else is under the x-axis. You can see there's a little bit tailing off there. This whole piece is under the x-axis. Just that little piece, just like we said, above the x-axis. It's a greater than 0 problem. Okay? All right, so I showed you what the problems look like. I showed you how you can rewrite them all as something is less than 0 or something greater than 0. I told you that means above or below, respectively. And I told you how to use a number line to solve it and to visually confirm it after graphing the whole two-dimensional plot. Okay? It's good now.